Welcome to the channel. I'm Ashwini. In this video, I'm going to explain about the 3-bit binary to gray code converter using system Verilog. First, what does 3-bit binary to gray code converter means? It is a simple combinational logic circuit that converts a 3-bit binary number to its gray code equivalent. This circuit can be implemented using the logic gates, such as XOR gates, because the conversion process primarily involves bitwise XOR operations. Now let us see the conversion. In this diagram, we have 3-bit binary numbers labeled as Q2, Q1, Q0, and we are converting it into a 3-bit gray code, also labeled as Q2, Q1, Q0. Binary code is shown on the left side and gray code is shown on the right side. Step 1. The first bit of the gray code is directly copied from the first bit of the binary number. Step 2. The second bit of the gray code is computed by XORing the first bit and the second bit of the binary number. Step 3. The third bit of the gray code is computed by XORing the second bit and the third bit of the binary number. This is the steps for the conversion. Now let us jump into our coding part. First, I am going to explain the test bench code line by line. The first line defines the module named tb_binary_2_gray, which serves as the test bench for the binary to gray code converter. Second line declares a 3-bit logic variable binary, which will be used as an input to the UUT. The third line declares the 3-bit logic variable gray, which will store the output from the UUT. Where the fourth one, binary to gray UUT, instantiates the UUT and connects the binary and gray signal to the corresponding ports of the UUT. The initial begin line starts the initial block, which contains the simulation control statement and the test sequences. $dump file specifies the VCD file. The $dump pass dumps all variable changes for the entire test bench into the VCD file. $display the header binary and gray. Now for loop starts a loop that iterates through all possible 3-bit binary numbers 0 to 7. Now binary equal to I assigns the current loop iteration value I to the binary input signal. Hashtag 5 waits for 5 times unit to allow the output gray to be updated based on the input binary. $display the current binary input and its corresponding gray code output in the binary format. End ends the for loop after all binary inputs 0 to 7 have been processed. $finish ends the simulation after all input have been tested and displayed. Now the second end ends the initial block. At last, end module ends the test bench module. Now I am going to explain about the design code line by line. The first 4 line defines the module named binary to gray with the 3-bit input binary and the 3-bit output gray. The fourth line always com begin declares an always com block, which will execute continuously and automatically whenever the input binary changes. Now the next line gray of 2 equal to binary of 2. The most significant bit of the gray code is the same as the most significant bit of the binary input. The next line gray of 1 equal to binary of 2 cap binary of 1. The second bit of the gray code is calculated by XORing the second bit and the most significant bit of the binary input. The next line gray of 0 equal to binary 1 cap binary 0. The LSB of the gray code is calculated by XORing the second bit and the LSB of the binary input. At last end ends the always com block. End module ends the binary to gray module. After simulation process, we will get our EP waveform. Binary 2:0 indicates 3-bit binary input showing its value over time. Now gray of 2:0, this represents the corresponding 3-bit gray code output signal also shown over time. I 31:0. This might be an additional signal used internally, possibly for indexing or tracking state or in the simulation. Time scale. The time scale on the top indicates simulation time, which marks at interval of 2 units. Coming to the summary, the waveform output visually represents how the 3-bit binary number transition through all possible values, along with the corresponding gray code values produced by the conversion logic. Each transition shows the relationship between binary input and their respective gray code outputs, confirming that the converter operates correctly according to the design specifications. Thank you.